I'm Danny, my partner Abby, and ours is the DNA processor. Sorry, Danny and Abby.
So the agenda for today is we're going to go over the introduction, then we're going to go over our instruction set architecture, then we will explain our enhancements, which are listed as DJNZ, swap, rotate left, rotate right, push and pop, and jump carry, and then we'll go over our hardware and block diagrams.
Good.
So we're going to start with our introduction, and we're going to go over the purpose of our project and then our system requirements. So for our purpose, our project is to develop a complete RISC 32-bit MIPS processor with an enhanced instruction set. And as I mentioned before, the enhanced instructions that we added are decrement and jump not zero, jump if carry, push, pop, swap, and rotate left, rotate right. The system requirements that I'll go over are the memory architecture, the register sets, the data types, addressing modes, and the input, output, and interrupt capabilities.
So this is a Harvard architecture. Just quickly, there are separate memories for the instruction and data memories.
The memory structure, so for our address space, it's a 32-bit address space with a minimum of 1,024 words for running our code execution. And both instruction and data memory modules are byte addressable, where each memory location holds 1 byte. The integer register sets that we have are 32 registers. The register numbers are to the left, and then the hex numbers are right beside them. The number of each register is the count column. And then we have the names listed and the uses and whether or not they are preserved on calls. The registers that are not user accessible are the program counter, and it's a 32-bit size. The instruction register is very similar with load and increments, and the flags register is listed here. We have our interrupt enable flag, carry, overflow, negative, and 0. The data types that we support are 32-bit register size. We have signed integers and unsigned, and you can see the hexadecimal and decimal ranges in the negative column as well as the positive column over here. Addressing modes that we support are immediate, 16-bit, 26-bit, register, direct, and indirect. For the immediate modes, so the 16-bit immediate addressing mode allows for 16-bit immediate values to be used in certain instructions. And so we have the instruction example to the left and the example RTL to the right. 26 bits, really just an overview. We add the address and the register and add it together and store it into a separate register. These are the register modes for direct. We're using, it is when the registers contain the operands in the instruction. Example, RTL and the instruction are below. Indirect as well, just a quick overview, is used for store word instructions. I/O capabilities, the minimum I/O capabilities are input-output instructions, and they are access a I/O module, which is 1K by 32. It receives an interrupt acknowledged from the CPU and also sends an interrupt request to the CPU.
So there are the 4 different types. So there's the R, I, and J type, which is what everyone has, and then we have our enhanced type. So I'm just gonna quickly go over the R type. It's just the opcode on the left, and the function, and then RS, RT, and RD. And the I type is just the opcode here, the first 6 bits, RSRT, and the media value is 15 to 0. And then again, jump is just the opcode, and the 25 to 0 is the jump address. So for our hardware diagrams, there's the data memory and the I/O memory, and these buses that interface them are tri-state, so there's no bus contention. And this is just a quick overview of our CPU module. It just inside is the instruction unit, the data path, and the control unit. So this is something we did have to add. We added this sign extension 15 because I needed this to do the decrement jump not 0 and the jump carry. I'll go over that a little bit more when we get to those slides. Yeah, I guess that's it. And this is our NG data path. What changes I made was I expanded the demux because I needed the S address to be able to write to the register file. And I also added this smux for this ALU here. It wasn't used in our enhancements, but I thought it'd be a good idea to add it just in case I wanted to do any future enhancements, so I can wrap ALU out back around and into the S input of ALU. And again, just going over, I added the RS as a write address.
This is also an addition that we did, is we had to add a barrel shifter to our design, and we implemented that inside of our ALU, and yeah, that's the diagram for it.
Again, these are the enhancements we're doing. So we have 2 types basically. We have an R type, and then this is the J type. So because we need 1F to do, for the opcode, just to know that it's an enhanced instruction, and the function code will be here. Now for the decrement jump not 0 and the jump carry, because we're kind of handcuffed with the 1F here, and I needed this for the function code, the jump offset is only going to be bits 20 to 6, so it's just going to be 15 bits. And it's implemented like the 8051 instruction set, where it adds the offset to the PC and not how we do the jumps. So first I'm going to go over the push. It is a pre-decrement, so it goes through the fetch, decode, and then on the 3rd state, the ALU out will decrement the stack pointer by 4. And then on the 2nd state, it pushes whatever is in RT, which is the value you want to push onto the stack. And in that same state, I write back to the register file the new value of SP.
Mm-hmm.
And for POP, this one did require more states to do.
Right.
Because it is the post increment. So on the 3rd state after fetch and decode, the ALU out is holding the stack pointer. And after this state, we load D in with the data memory, whatever we wanted to pop off. In the 3rd state, we write that back into the RT, which is where the register we wanted to pop it into. And then in this state is when I increment the stack pointer, and then I write it back into this state here. This is just showing the verification. It is lengthy, but it's just because I wanted to show that the interrupt still worked while adding the enhanced instructions. So what I did was we added so I pushed the register R5, which holds 5A, 5A onto the stack pointer. Immediately after that, I popped it off into the register R25, which is a little tough to, it's in the next slide here, so here it is. So I pushed it onto this register here, or I popped it off of it, I'm sorry. And then immediately after that, I pushed onto the stack the value of R2, which is H7654321 into 3F8, which is the next spot. And then when I write back the stack pointer, that's the value right there. So for rotate left and rotate right, they are very similar. After the decode state, the barrel shifter is what actually does it. And we added 2 new function selects for it. So this rotate left can rotate as many times as you want for the shift amount. And then after this state, it just goes back to the write back ALU, and it goes back to fetch. And to verify this one, it is very similar to the way you did the verification for the shift left, shift right. I load. This is the initial value that I'm going to shift, and then this is just the loop counter, and this right here is going to be the memory pointer. So it's rotating left 2 bits each time. It decrements increments the memory pointer, decrements the loop counter, and then just writes back. And these are the correct values over here, which we have verified on this left hand on the set right here. And for our rotate right, this is very similar to rotate left. After the decode, it goes to this. Again, it can rotate as many times as you want for the shift amount, and it goes back to write back ALU, and then back to fetch. And I'm going over decrement jump not 0 because I do verify that these work in the same data module, or in the same instruction module, I'm sorry. So for decrement jump not 0, after decode, the register that we're going to decrement and then check if it is 0 or not is in RS. So that's what this, in the third state, RS gets decremented by 1. And then it goes to the decrement jump 2 state, which checks that 0 flag. So if the 0 flag isn't 0, then it's going to add that sign offset 15 to 0. And then it's going to, in the same state, it's going to write back that register value decremented by 1. But if it doesn't, if it is 0, then it just deasserts all signals and falls through the next instruction. This is how we verify it. Again, this is the initial value, but instead of having so this is the memory pointer, and then here, this is going to decrement the loop counter and then check it at the same time, and it's just going to jump back if it doesn't equal 0. And here are the values that we verified that are correct on this side here. And for the swap instruction, this just swaps. It allows you to swap 2 registers. The registers that are going to be swapped are RS and RT. So simply, after decode, the swap state is going to, LUL is going to hold RS. And then in this state here, the value of RS is going to be written into the register that's in RT. And in this same state, RT, what was in RT gets pushed to ALU out. And then immediately after this state, the value that was in RT is going to go into RS. And I'm just showing here that the swap verification did work. So initially, R1 is loaded with all Fs, R2 is with 8765431, and R3 is just hex 10. So first we perform a swap on R1 and R2, and then immediately after that, we swap R1 and R3. So you can see these are the correct values after they do swap. And the final instruction we added is the jump carry. This just checks the carry flag, and if the carry flag is high, then it's going to jump. If it's not high, it's going to fall through. This doesn't change any of the flags at all. So this is only 3 states. It goes fetch, decode, and immediately checks that carry flag, like I said, and it'll load the PC with that jump address. If the carry flag is 0, it'll just desert all signals and it'll just fall through to the next instruction. And to test this, I loaded R1 with all Fs, R2 here with 0s, and then R3 with this value here, 100000000. So when I add R1 and R2, the carry flag should be low, so it shouldn't jump. But when R1 and R3 are added, the carry flag will go high, so it should jump. So the way I tested this is with the fail flag and a pass flag. So first I add R1 with R2, and then here I check the carry flag, and it shouldn't jump, and it doesn't. So this R14 here will be filled with all Fs for the fail flag, and R15 is the pass flag here with all zeros. So it doesn't jump here, so the R15 is loaded with Fs. So when R1 and R3 get added, the carry flag is high now.
Yeah.
And it will jump to this part of the code, and it'll set the pass flag and R15 to all zeros. And that's it.
Any questions? You did a good job presenting. That's excellent.